Good afternoon, biology students. Today we're going to cover part of Chapter 2. As I said, one of the days that we had met in person, Chapter 2 is on largely a review of some of the chemistry aspects from physical science that you need to understand for biology. So we're going to go through here in the next 15 or 20 minutes, roughly a chapter or a chapter and a half of last year's physical science. Okay. So feel free to come back and watch parts of the video over if you need some more clarification. All right, so this section is called The Nature of Matter, aka Physical Science Review. And the first thing we need to make sure we remember from last year is what an atom is. Okay, and I remember teaching ninth grade physical science, and kids had just came from earth science in middle school, and before that they had life science, and cells and atoms would get confused, and that's going to happen again this year. But remember, atoms are not living. Okay, they're the basic building block of matter, and this idea goes way back to the time of the Greeks when Democritus called or used a term called atomos, which meant uncuttable, and he was trying to describe the smallest piece of something, like piece of gold or whatever, and he knew that it could get so small that you couldn't cut it smaller. And so this is where we get the word atom from our understanding of that type of thing. And you guys learned about atoms last year, and recall there are three parts to an atom. There's protons, neutrons, and electrons. And we need to make sure we understand the differences, not only in charge but location. And so we'll start off with protons. Protons start with P. A great way to remember that they are positive. These are found in the nucleus. Here we see a red proton. It's just color coded so we can tell there's two different types of things here in the nucleus, or the center of the atom. The other particle found in the nucleus is the neutron. Okay. Now, right away, kids assume, oh, P was positive, so N must be negative. Don't follow that method of thinking. Instead, use the word neutral to remember neutron. Neutral means no charge. Okay, so they're not positive, they're not negative, but they're also in the nucleus, and those two are about the same size. They're roughly similar mass sizes, and scientists use EMUs as a unit. So we're going to look at that here in a little bit. A unit of one each of those particles. Then we also have electrons. Electrons are the negatives, and they are not in the nucleus. They're actually out in the area around the nucleus called the electron cloud. Okay. Here we see an atom with 3 electrons. Okay. One thing that's not accurate is the scale of this model. And you probably learned that electrons are much smaller than their protons or neutrons. Electrons are like 1/2000th the mass. And so it's hard to illustrate that in a picture. Instead, people tend to think they're the same size, but they're not. These are much smaller. They're negative. So they're attracted to the positivity of that nucleus. And so they don't escape. They move very quickly in all directions and give an appearance of a cloud. Okay. A bonus to you if you were thinking that this is lithium, because it is. There's 3 electrons. We'll show you how to tell that here coming up. All right. So how do you know how material is structured? If everything's made of atoms, how are we different from a piece of iron or water or something like that? Well, we take atoms, and if we have a bunch of the same kind of atoms, like the one in the previous picture, okay, and we said that was this one here, lithium. We have millions and millions and trillions of those atoms together, and that's all we've got, then we've got what's called an element. Okay, it's a pure substance. It's pure throughout, and there's roughly, as you can look on this picture, on this diagram here, periodic table, 118 identified elements. Okay, so roughly everything that we know as matter, everything we've identified or discovered, is made of 118 ingredients. Okay, and then we can get these in various combinations. So we just don't take these ingredients and leave them alone. Things can happen to them. Living things, an animal or a plant, contain about 24 of those 118. So we've got about a quarter of the total elements, I guess, in a living thing. Okay, others are found in other portions of the universe. When we look at the periodic table, we see symbols or letters or letter combinations in each box. And this is basically it's kind of like abbreviating a state. It's a quicker way to show what we're talking about. It's less cluttered. We can use them to talk about other types of matter, which you'll see soon. Now, some of these symbols are pretty understandable, or common sense would go, oh, yeah, that makes sense. Like oxygen is an O. Okay. But then other ones don't seem to follow that, such as mercury, right here, Hg. Okay, there's really no H or G in mercury. Some of those have come from the Latin names. Elements that were written about in texts and books many, many years ago, and they were named with using Latin, and we've just kept those symbols in use. Kind of cool history there. Also, we see a whole number in each box, and the periodic table is actually arranged in that number. We see 1, 2, 3, 4, and it'll go numerically. It's called the atomic number. That number indicates something very important about each element. It tells us the number of protons and electrons. So it tells us the number of positives and negatives in the atom. So using carbon as an example, carbon, which we'll talk about a lot this year, is number 6 on the periodic table, which means it would have 6 protons in the nucleus and 6 electrons in the electron cloud in each atom of carbon. Okay, and it will always have that. And we say, well, what if it had another one? Okay, if it had another one, notice it wouldn't be carbon anymore, it would be nitrogen. Okay, and that's kind of the very interesting thing about the periodic table, and how the uses can change so dramatically from one to the other. Probably talked about that last year, just going from 7 to 8, 16 to 17 dramatically changes what the material is and its properties, how it looks, how it behaves. But things can get a little tricky too. So isotopes, we will talk about that throughout the year at various times too. But isotopes are important in chemistry, physical science, biology. It's the same element, but it's got a different number of neutrons. Now remember, neutrons don't have a charge. And because they don't have a charge, they don't influence the characteristics or the properties as much as protons and electrons do. And so on periodic tables, there's also another number. And this number usually is in decimal form. Here, we're looking at it in a more simplistic way to understand isotopes, but typically it is in a decimal form. And that's called our mass number. And it's the total number of protons and neutrons in an atom. Okay. Now remember, protons and neutrons are in the nucleus. They're always either you have one or you do not. Okay. So you either have 1 as your mass number or you have 0, yet we get a decimal. And some of you probably know how that was achieved. It came to be because masses are just like our masses. If we were to measure our body masses, we're not all the same, right? We probably fall in a range, but um, every one of our masses is different. Well, it's kind of like that with atoms. Carbon, for example, they don't all weigh the same. Okay, they can vary a little bit, and the reason they can vary is because they can have different numbers of neutrons. Okay, so for instance, in carbon, we have three isotopes: carbon 12, carbon 13, and 14. And those numbers refer to their total mass. Okay. Since the electrons, the protons, which are based on the atomic number, always need to remain at 6, carbon, yet the neutrons can vary. We can get different types of carbon. Okay, so look at any standard periodic table. The mass of carbon is going to be very near 12. 12 point something, but it would round to 12. And so what we can get from that is that every atom of carbon is going to have 6 protons because of the atomic number. Every atom of carbon is going to have 6 electrons because of the atomic number. And those positive and negatives are always going to be equal and balanced. Most of the time, carbon also has 6 neutrons, but there's times when it can have 7 neutrons. And it makes it just a little heavier. It has an atomic mass of 13. Okay. So you're adding 1 there. Carbon 14. How many neutrons do you think carbon 14 would have? If you said 8, that's correct. 6 protons, 8 neutrons, and 6 electrons. And you might say, well, why isn't the electrons figured into that mass? Remember, they're so small. Okay. So we use these isotopes for quite a few things in biology. Cancer treatment's one example. Carbon dating of rocks is another example for us to try to age fossils and past living things. All right, now, not everything is a pure element. Um, Many living things well, many things in general, I guess, are made of compounds. That's when 2 or more elements combine chemically in a definite proportion. Okay. Greatest example is something that you guys eat all the time, part of your diet, something you need for your health, something you might put in your popcorn or your fries just because it tastes good, right? Salt. Okay. Salt is actually called NaCl, and that's a compound. And we know that because we have more than one symbol, element symbol. Na is the symbol for sodium, Cl is the symbol for chlorine. And sodium chloride, sodium and chlorine bonded, is called table salt. Okay. Now, when you look at their properties individually, it's pretty amazing. Okay. Here's sodium. Oh, looks like some dull metal or clay. It actually kind of looks and seems like metallic clay. But if you've ever seen pure sodium, you've probably seen it react. It's very reactive. It will react with oxygen, water. This is a metal that will, if you throw it into water, will actually explode. Okay. Now that's in its pure form. Okay. Chlorine, same thing. It might say, well, we use chlorine in our pool. Okay. Right. You do. But you probably use it in a different form or different strength. But in pure form, it's a green gas. Very, very dangerous. Poisonous. Okay, so basically both these are very dangerous if you had them separate. If you put them together, salt is not really that dangerous, right? Yes, you can have too much. Might hurt if you get it in your eyes. Might be dangerous to a soft-bodied animal because it can dehydrate them. But the characteristics are completely different from their parts. So um, formulas and even symbols give us a recipe of what we've got. So to get salt, we need even numbers of Na and Cl, 1-to-1 ratio. All right, last thing we have to talk about is bonding, and bonding comes in 2 kinds. at least for today. Okay, two main kinds: ionic. And ionic bonding is when one or more electrons are transferred from one atom to another. Okay, so transferred means we take one electron from an atom and we give it to another one. Okay, so we're changing the numbers then. Remember, electrons are negative, so you kind of have to remember that to get these straight. A positive ion is one that loses an electron. Okay, so if you lost an electron, let's say you're carbon and you have 6 negative charged things and 6 positive charged things, and I lose one of my negatives, now I only have 5 negatively charged things, but still 6 positives, it means I'd be positive overall. So I would be a positive ion. If you gain the electron, you become a negative ion because electrons are negative. Okay, good way to remember that is this comic here. We have 2 atoms, and this one says, I lost an electron. The other one says, no way. Are you positive? Right? It's funny. And how this works then as bonding is that now we get, okay, let's look here. Here's the sad one. He lost his electron, right? This one's positive. If we have the one that gained it, I don't think we have that in this case here. This is a totally different one. But one that gained it would become a negative, and positive and negative attract. Opposites attract. And this is how metals and nonmetals bond. This is exactly how salt comes to be, through ionic bonding. Okay. Get a metal here, which will become what we call a positive ion. Make sure I did that right. Yes. And chlorine, which is a nonmetal, and which will become a negative ion, and they bond together. Other kind's called covalent, and my mistake, I did not highlight this. I will for future use, but I like to highlight the vocab words. I think it just helps you to draw yourself in there. So it should be highlighted. Covalent bond. This is when electrons are shared between atoms. Okay, so they're not fully given or lost or gained. We're not like that poor atom on the previous slide who was all sad because he lost his electron, right? I mean, come on, keep track of your stuff. Here's where we share it. Okay, in covalent, it would be like, well, I'm using this electron, but I'll let you use it as well. Okay, right? Cooperate, share, work together, right? So this happens with nonmetals, which coincidentally is the many of the elements found in living things are the nonmetals. Okay, oxygen and carbon and nitrogen and things like that. Anytime we combine elements together or atoms together, whether it's ionically or covalently, we get what's called a molecule. Okay, so like water, we don't have atoms of water. We have molecules of water, but we do have atoms of hydrogen and oxygen that come together to make that molecule. So here's from simplest to more complex. Here's the simplest diagram. We see a H, so a hydrogen atom, an oxygen atom bonding. We get a water molecule, which has this upside down Mickey Mouse look to it, Mickey Mouse face. Three-dimensionally, we would see how those they aren't stuck with a little stick there. They're bonded together. Okay, and planetary model, this showing the electrons. Okay, and oxygen, okay, being 8 protons, 8 neutrons, and should have 8 electrons. Okay, having 2 there, and then 3, 4, 5, 6, then one of these, and then one of these for 8. Okay, and then each of these hydrogens has 1 proton, and I wish it said like 1p there, but whatever. It's one positive, so it's a plus. No neutrons, and they did have one electron here and here, we'll say. Okay. Now, hydrogen is sharing one of the oxygen's electrons, and the oxygen are sharing the hydrogen's electrons. So we get what we call a full shell. This is what atoms are trying to do. They're trying to become stable. Atoms by themselves are non-stable. Do you know anybody named Adam? Huh? Their goal is to become stable. Okay. Uh, actually, Adam Sandler, is he stable? Okay. One of my favorite actors. Anyway, Atom's trying to become stable, and so when we get a full shell, if it has one shell, then we need two. Okay, we already had that here. That second shell needs 8 to be full. There it is. It's full. Okay. Mission accomplished. Okay. All right. So hopefully some of this stuff correlate goes well with the How Stuff Works water video. I think it's just a cool video, and it actually goes to show some of the chemistry there. And please fill out the Google form on the science review. And thanks for watching.